We have studied a particular one-dimensional system, that is the harmonic oscillator, in some detail in the last several videos. Okay, but here we want to talk about one-dimensional systems in general. So I'm not going to assume anything specific to a given one-dimensional system. I'm going to treat it to be fairly general, and we'll try to see what all we can say in general for one-dimensional systems. Okay, so that's the task we have in front of us. So if I want to write down the Lagrangian of a one-dimensional system, which let's say is which I'm going to label by a coordinate q, the generalized coordinate q, then the Lagrangian would be, as you are already familiar, would be the following. So L will be, the Lagrangian is half A of q dot square minus the potential energy, which is a function of q. Okay, remember that there will be a function here which depends on q. Okay, this is because you have gone from your Cartesian coordinates to generalized coordinates q. Okay, now here you see the time does not appear in the Lagrangian the way I have written here, which means that this will have integral of motion, or what we call Jacobi's integral, okay, which will be a conserved quantity. So that energy function or Hamiltonian function, that will be a conserved quantity, and you can immediately obtain H. I think this is what we called earlier, HQQ dot, and this will turn out to be A of q dot square plus U of q. And for the system, this will be constant throughout the motion, and it will be some number E, okay, which we call energy. Now frequently we are going to encounter a situation where the AQ is a constant, which you have seen earlier in our several discussions during studying harmonic oscillators. So frequently we were having A of q to be 1 or some constant. So let me write this. Frequently often we will encounter A of q to be a constant. Okay, let me call it A naught. Okay, and what I can do is I will have A naught. I can do a scaling of time, and I can take yeah, let me see. Yeah, so let's do it here. So I have half A0 dq over dt square. Okay, and if I define I can just write it like this: half dq over d t over square root of A naught square. Okay, that's the same thing as above. Perfect. So if I define my new time to be like this, okay, then you can see that I will get rid of the A naught. Okay, so under a time scaling I will be able to write the Lagrangian as half q dot square minus U of q. Okay, that's good. And now your Hamiltonian would be, or the energy function would be, H will be half q dot square plus U of q. Perfect. Now we want to solve this system in general, but I don't need to set up the equations of motion using Euler Lagrange equations, because I can use this integral of motion, okay, and set up a first order differential equation. Okay, so let me write down this thing. This is I will to solve this problem, we can use the first integral of motion. Okay, and remember this is a first order differential equation. Okay, so let's do that. So here I have half q dot square plus u equals e. E is a constant. All I have to do is take u to the other side and take a square root, and then I get a expression for q dot, which I can integrate. Okay, that's what I'm going to do now. Okay, so as I said, I can write the previous equation which I had like the following. So I can write half q dot square equal to e minus u of q. Okay, note that even before I start integrating things, look at the left hand side. Left hand side is a square of a real quantity, right? Okay, because q is real, so q dot has to be real, which means that this can never be negative, which says that the total energy of the system should always be greater than the potential energy that the system has at any q value. I mean, if a system is at some q, then the system should have a total energy which is more than the potential energy that the system has at that point. Okay, so e minus u of q should always be greater than equal to 0. Okay, so that's the constraint we have, and as you may be aware that this is not necessarily true in quantum mechanics. Okay, but classically you see that this has to be obeyed. Okay, now let's start looking at how we'll get a solution. Let me integrate this equation, this one. So I get q dot 2 e minus u of q. Okay, and that entire thing will be in a square root, and I can integrate this. So you write this as dq over dt. So I take dt. I mean, I can jump one step. There's no need to write again. So basically, I'm taking dt there, and I'll bring this expression below dq, and I'll do the integral, which will give me t to be dq over 2 e minus u of q square root, and there'll be a constant of integration. Okay, that's what you get, and let me just put the integration variable to be q prime. Okay, yeah. Now this is a, I mean, if this this provides a solution, so I can know where the particle is at. I mean, if I okay, before I say that, let's look at the following. You expect two constants of integration because your system is really described by Euler Lagrange equations, which are second order differential equations. Okay, so there should be two constants of integration. But now we have not really solved those, but does not matter. Whichever way I solve, if my equation is going to be described by a solution which will have two constants of integration, it should have here also. So as you may see, you already have those two, because one is a constant which you have got by doing the integral, and another one is E, and both of these you are going to control by your initial conditions, meaning these are determined by your initial conditions. Okay, so let me do a little bit more. I can write this as, so let's say I say that when Q is equal to, so I do away with this constant. Okay, I'll do a definite integral now. So I will put Q from t equal to 0 to Q of t. Okay, so this is a definite integral now. Okay, and this I want to choose to be 0. Okay, let's call this equal to 0. So what you have basically is the following: 0 to Q of t dq prime over 2 e minus u of q prime. Correct. Okay. Now, so if I can calculate this integral, if you are given a u of q, and you see it's only the potential energy that describes this system. Okay, so if you are given a u of q, you can do this integral and get t as a function of q. Okay, and in principle you can invert it. It may not be possible always, but you can invert it, let's say, and then you'll have the trajectory. But in any case, we call that the problem has been solved because we have t as a function of q in principle. Okay, that's nice, but what we will do now is try to say things in general by just looking at the potential energy function. Okay, this u of q, and as you'll see, a lot can be said for one-dimensional systems. Okay, without doing any integrals, without doing anything. That's my next task. Okay, so let me draw a potential energy graph. Okay, what happened? Yes. So along the horizontal axis we have q. Here on the vertical I have u of q, that potential energy. And in general, what you can have here is that the potential may have some places it takes a local minimum. At some places you can have maximum. The function could be going to 0 at the infinity. Okay, these kind of things can happen, and that's the most general feature you can put in your potential energy function. So I'm going to draw a graph here which will be depicting a general situation. So what I do here is I just choose the place where I have a minimum to be at the origin. Okay, the one of the minimum of this potential I choose to be at the origin, which you can do. Okay, you can always do so. And let's say the potential is not looking very nice. Okay, it's doing something. It goes, let's say, I don't want it to be more parabolic. Okay, something of that sort. So this is this is the most general situation. It has a maximum, minimum. You can have maxima here also. You can put several maximum here, but the general feature is this. Okay, So let's say my system is described by such a potential energy, and I choose initial conditions such that the total energy of the system E lies somewhere here. Let's say it lies somewhere here. Okay, so let me draw a horizontal line here. You will understand why I'm doing so. Maybe I can choose some color. Okay. Okay, so this is E. Okay, very nice. And let me also indicate these points. Let me call it QA, QB, QC. And I want to label these points as A, B, and C. Okay, and this point as E1, this point as E2. Okay, perfect. Now, you see, let's say you start your system with this total energy E, which I have specified now, somewhere in this region, okay, somewhere in this region. Now, if you do so, then because E1 is nothing to do with E1, but let's say you start it here or here, does not matter, and it's moving, let's say the system is moving in this direction, okay, so its Q is going towards QA. Now it will have a kinetic energy here, because of which it will be able to climb up to the point A, and at this place it will run out of its kinetic energy, because your potential energy will be equal to the total energy, so your T has to be 0. But there is a force which is still acting on in this direction, okay, so the system starts moving backwards. So this point is called a turning point. So the point A is a turning point. So the system starts rolling backwards, goes further here, shoots up to B, and it again runs out of kinetic energy, and it has to turn backwards, and so B is another turning point. Okay, so as you can see that if you have started somewhere between A and B, then the system is going to oscillate from A to B. Okay, it will keep oscillating back and forth between A and B, and it will have some time period T, which we can determine by doing those integrals, but that is what is going to happen. Okay, so that is one situation which can happen in a general potential. But let's say you don't start your system here, you start your system to the right of C. Okay, let's say somewhere here or here at some such values, and let's say your system is moving in this direction. Then what will happen is it will keep climbing up. By climbing, I'm just using the analogy with a hill or something, but it keeps climbing up the curve, and when it reaches point C, then it runs out of its kinetic energy, because your total energy is going to be U, but still there's a force in this direction, so it goes there and sees again another turning point, and it rolls back towards positive Q. Okay, and it never returns back, it just keep going on if there is no other maximum there, or if there is no maximum which is as big as this line E. So it will keep rolling down and it will be gone to infinity. Okay, that's what will happen. So your point C is also a turning point. Your point E1 and E2, as you already know, these are points of equilibrium. One is stable in this case, another is unstable, but this is all that can happen in this system. Okay, so one, it can oscillate back and forth in such a place, or it can go here and get lost to infinity. That's all. There are other possibilities which can occur if you choose a different kinetic energy or different total energy for the system. So let me try to get that one. Okay, let's see. Now suppose you start with a total energy which is equal to E2. Okay, so your total energy is E2, but you have started here, so you have put the system here where the potential energy itself equal to E2, so it stays there, nothing happens. If it is not disturbed, it stays there forever. Okay, so that is what's going to happen. Similarly, if you put the system here with energy equal to, in this case, 0, because you have chosen the origin to be here, then it stays there forever. Okay, so these are all possible motions that can occur in a one-dimensional system. Okay, let's see what more I want to say. Okay, I'll give you an exercise here. So what you have to show is the amount of time the system takes in going from A to B will be equal to the time it will take from going from B to A. Okay, so show that time taken in going from A to B is equal to time taken in going from B to A. Okay, that is what you should show, and all you have to do is use the equations of motion. You don't have to solve anything and think why this should happen. From your experience, you already know that this will happen, right? That this should happen, but what you have to do is show explicitly from equations that indeed this will happen. Okay, so let's proceed further. Let's ask what will be the time period of oscillation if our system is oscillating between A and B. Okay, and that's quite simple to say. What happened? Oops. Okay, something not very nice. Okay, let's add one more sheet. Okay. So time period of oscillation which is just the time it takes from going from A to B and back. Okay, that will be T. This will be dq prime over, this is what I wrote earlier, 2 E minus U of q prime. Okay, and then you have to integrate from QA to QB, and it will be the twice of it because it takes the same amount of time. Okay, and as you can see that the values QA and QB are determined by your the total energy that the system has, right? Because up to where this will climb will depend on the total energy that you give. So whether it goes only up to here and here or up to here and here, it depends on the total energy that your system has. Okay, so qa and qb are basically functions of energy. Of the total energy. Okay. Now let's take a specific example. Maybe I should go to the next slide. Or here itself. So I want to take this example. My system is the following. I'm taking a one-dimensional system described by the following potential. So here I take the potential to be symmetric, at least in this region, not necessarily parabolic. It is some function, but it is symmetric. And beyond that, it's not. So let's say it's like this, and this one is, let's say it goes whatever it does. But as far as, let's say, this point, this is, let's say, lying on a horizontal axis between point A and point B. So QA, QB, between these 2 points, it is a symmetric potential. Okay, so that's one assumption. So let me write it down. Potential is assumed to be symmetric between QA and symmetric about origin between QA and QB. Okay, that's the assumption. And let's say I start my system with some total energy E, and let's say the energy corresponds to here. And this point I call Q0. Okay, that's the total energy of the system. So what will be the time period of oscillations when the system is put in this place, in this location? So it has to go from here to there and back. That will be the time period. But you already know, because I gave an exercise, that the time it takes in going from here to there is same as it takes in coming back. Okay, but then I have on the top of it chosen the potential to be symmetric. Okay, which means the time it takes in going from here to here, okay, that is 1/4 of the time period. Okay, so here the time period T is 4 times the time it takes in going from 0 to Q0. Zero to Q0. I hope that point is clear. The sole reason why I took it symmetric around this was this symmetric. Okay, that's nice. And of course your Q0 is determined by energy. So let me write Q0 is a function of energy. Now what I want to do is the following. Let's define Q tilde to be Q prime over Q0. Okay, if I do so, then my dq prime is Q0 dq tilde. Okay, that's good. So what is my time period now? Time period of oscillations. This is 4 times integral 0 to 1, because when your q prime is q0, your q tilde is 1. Okay, so I have removed the dependence on energy from the limit of integral. That's fine. Now my dq prime is q0 dq tilde divided by 2. E is a constant, but E is equal to the value of the potential energy at this point, right? So E is equal to U of Q0. Let me write that, U of Q0 minus U of Q prime, and this entire thing sits under a square root. Okay, that's good. Okay, no, I should not write a Q prime, I should write Q0 Q tilde. Q0 and Q tilde here. Not looking very nice, so I'll clean it up. Q0 Q tilde, and this is in the square root. All looks good here. Okay, fine. I can write this as T equal to 4 over square root of 2, 0 to 1, dq tilde over u of q0 minus u of q0 q tilde. Okay, that's correct. And then you have 1 over q naught square, and this entire thing in the square root. All I've done is put this q0 into the square root here. That's all, nothing beyond that. Okay, so note that in general this time period of oscillations will be a function of q0. Okay, and this q0 is really the amplitude of oscillations, right, because that is the maximum distance it will come up to, and which is determined by the energy, as we said before. So in general T is a function of q0, and remember q0 is the amplitude. Or I can also say that T is in general a function of E, total energy E, right, because q naught is determined by E. Okay, now let's ask whether it is possible to choose the potential energy to be such that T does not depend on q naught. Okay, and it's clear what we should do. If this entire function thing is not a function of q naught, then the denominator should not be a function of q naught. So what we are asking is, if we look at uq0 minus u of q0 q tilde, okay, 1 over q0 square, that's what you had in the denominator. If this thing, which is a function of q and q0, let's call it f, if this were not dependent on q naught, then the time period will be independent of q naught. Then time period of oscillations will be independent of the amplitude. Independent of the amplitude of oscillations. Okay. Now, for what potential will that happen? Clearly, if I choose u of q0 or u of q, let's write, to be something, some constant times q square, then clearly you will have a 1 over q0 square from here. This will be proportional to q naught square. This will also be proportional to q naught square, which will cancel with this q naught square, and it will be independent of q0. So you see, for quadratic potentials, the time period of oscillations is independent of the amplitude and also of the energy of the system. Okay, if the potential energy of the system is not quadratic, then this is not true. Okay, so that's nice. So let's write it down. Whatever, if this, then that. Okay, so only for quadratic potentials T is independent of amplitude or energy. Okay, that's good. And this is the reason why when we studied simple harmonic motion or small oscillations, our time period was independent of amplitude or the energy of the system, because we were under an approximation in which the potential energy was approximated to be quadratic. Okay, but the moment you deviate from quadratic approximation, you will see that the time period will depend, and that's what we will look at in a few examples, which I will take up next.